Alright, today's lesson is on the idea of what's called related rates. And the idea behind related rates is that in real world situations, you have something changing with respect to something else, and it's changing at different rates. An example of this would be the following. If I had a cone that was full of water, and it was draining out. So it's full of water, and the water is draining out at some rate of speed. The cone's eventually going to be empty. Now, over time, as it empties out, the volume is changing with respect to the height of the water, the radius of the cone. All these are changing as time changes, as time goes by. And so these are rates that are related to each other. And so if we wanted to talk about how these rates are related, we would use implicit differentiation to find the rate of each one of these guys. And so what I'm talking about doing is taking the derivative with respect to time. Now we don't see time anywhere in this equation, but most related rate problems are with respect to time of the volume and determining that value as we look at the derivative with respect to time of the radius and the height. Now all these are changing as the water drains out. Alright, and so this falls back to the topic, our last topic, on implicit differentiation. If I want the derivative of v with respect to time, it's just going to be a dv dt. There's no exponent, there's no coefficient, so I'm just talking about the derivative of v with respect to t. Now understand, dv with respect to dt is talking about the slope, the rate of change of the volume at some moment in time. And that's going to be equal to, we can bring our pi thirds out and deal with these two guys right here. Let me erase that. Okay, we can deal with these two guys right here. You should recognize this. This is the multiplication of two different differentiable equations. And so if we think back to our rules for multiplication, we take the derivative of the first, we take the derivative of r squared right here. The derivative of r squared is 2r. And because there is no r in our derivative statement, we have to add the dr dt to the end of it, just like we did on implicit differentiation. And then that is being multiplied by the second term, which is right here. So we're just multiplying by the h. So remember our multiplication, it was f prime times g plus f times g prime. Alright, so here's our plus statement right here. There's our plus. And so now we're going to multiply by f, right there, doesn't change a thing, times the derivative of h. Well, again, h has no exponent, it has no coefficient. The derivative of h is going to be dh with respect to t. So right there, that is how we write the derivative of h with respect to time. And that, again, that's our multiplication rule for differentiation. So if we begin to simplify right here, this h is really just going to wind up being like a coefficient, so it can come into the front right there. And so we'll have a 2rh, 2 times radius times height, times the derivative of the radius with respect to time, plus r squared times the derivative of the height with respect to time. And that is our expression. That is the derivative of this original equation right here with respect to time. Each piece has been derived with respect to time. Now at this point, it's not very useful because we don't know enough information. We just know how the things are related. And so what we're looking at here is the relationship of the change in volume. So right here, the change in volume, the rate of speed the volume is changing, is equal to pi over 3 times 2 times radius times the height times the rate in speed at which the radius is changing, plus r squared times the rate in change of the height. All of these are slopes of 3 different equations. So if I had an additional piece of information, I could then use it to find the other two. So let's take an example. Suppose that a pebble has been dropped in a pond and creates ripples. The radius is increasing at 1 foot per second. So here's a picture of what we got. You dropped a pebble in the water, and so you have a ripple, and then a second later, and then a second later, and each one is a foot further out. When the radius is 4 feet wide, how fast is the area changing? How fast is the area of our circle changing right there? Well, here's our formula. Pi r squared, that's the area of a circle. I just told you that the radius is increasing at 1 foot per second. So dr, the derivative of r with respect to time, the slope of that radius equation is 1 foot per second. So we want to find the derivative of the area, how fast the area is changing at some point in time, specifically at the point in time when the radius is 4 feet. How are we going to do that? Implicit differentiation. We want to take the derivative of the area with respect to time, and that's going to be equal to the derivative of pi r squared with respect to time. Now again, notice, there is no time in either one of these two equations. So these are all going to be implicit differentiation problems. The derivative of area with respect to time, area has no exponent, it has no coefficient, it's just dA over dt right there. Is going to equal to, what's the derivative of r squared? We know that r squared, we know how to derive that. Bring the 2 down, subtract 1 from the exponent, and you're left with 2 times pi times r. And again, because this is the derivative with respect to time, we have to add the derivative of radius with respect to time right there. And if we simplify that out and plug in what we know, we can find an actual answer. What do we know? We know that dr, so I'm going to erase everything here. We know that the derivative of r with respect to time, right here, is 1 foot per second. Do we see a dr with respect to time in this final equation we have down here? We're going to plug it in right there. That's going to become that 1 right there. We also know that we're interested in the point in time when the radius is 4 foot. That's going to go in right there for our radius, 4 foot. Then it becomes simple math. We're talking about 2 times pi times 4 times 1. Our area is increasing at a rate of 8 pi feet per second at the point in time when the radius is 4 foot wide. That's the point of related rates. To be able to use one information you know to find how fast the other ones are changing. Here's going to be our homework we're going to do in class tomorrow. These are not trivial problems. You might want to take a look at those tonight and be ready to tackle them.